Hi, welcome. My name is Sid and I'm a Senior Solutions Architect with AWS. And today we'll be talking about how you can go global with AWS multi-region network services. Enterprise customers are building modern applications which are characterized by massive scale. We're talking about millions of users, petabytes of data volume, millisecond, microseconds performance latencies, and most importantly, the user base is global. So to serve your user base, you're deploying application stacks in AWS regions globally. The number one requirement is connecting these application stacks so that they can communicate and synchronize data. Next, you want your corporate data centers to be able to communicate with your AWS resources. And finally, you have end users and you want to expose your applications to them with lowest last mile latency. And this is what we'll be focusing on in today's session. We'll see how you can use inter-region connectivity to connect AWS regions. We'll see how you can leverage global hybrid connectivity to connect your data centers globally to AWS regions. And finally, how you can expose your applications to your end users, ensuring lowest latency. Let's get started by talking about inter-region connectivity. Now, the easiest ways to connect VPCs which are located in different AWS regions is to use VPC peering. You create a peering connection, which is a fully managed connectivity by AWS. And all you need to do is configure your VPC route tables to leverage this peering connection. Now, keep in mind that VPC peering is point-to-point connectivity, which means that if you want 4 VPCs to talk to each other, you have to create a peering connection between each and every VPC. Hence, creating a full mesh design. Now, at scale, when you're connecting tens and hundreds of VPCs together, managing a full mesh network can be challenging, and you might start hitting peering limits. So, at scale, we recommend you use Transit Gateway. Now, for those of you who don't know what Transit Gateway is, it's a fully managed networking services which sits at the center of your network connectivity and acts as a hub. It connects thousands of VPCs together, and it can also connect your on-premises networks using AWS VPN or Direct Connect. Now, Transit Gateway is a regional resource, so it is confined to an AWS region. So if you want inter-region connectivity, you'll have to peer Transit Gateways together. Now, Transit Gateway connectivity and VPC peering connectivity across regions is over Amazon's global backbone. So if you deploy transit gateways in 2 different AWS regions, all of that traffic which is flowing is on Amazon's global backbone. Now let's take an example and understand how peering works. So here I have transit gateway and VPCs deployed in multiple AWS regions. Let's peer them together. So I peer US West and US East transit gateway. Then I peer US East and EU West transit gateway. Now, if I wanted to send traffic from US West to EU West, I can send the traffic first to US East and then route it to EU West. Now, this is a totally valid configuration and you can do this. But this is not a best practice because you are creating a regional dependency. If US East transit gateway goes down, you lose connectivity between US West and EU West. Additionally, you're adding an extra hop. So you're paying for additional data transfer charges and you might add more latency as well. So what you really want to do is create a peering connection directly from US West to EU West and send traffic that way. Now, following on the same principle, let's just create more peering connections. And the idea here is between transit gateways, there will be a full mesh of peering connectivity. Perfect. Now let's take a closer look on how peering can be configured. To explain this, I'm taking an example where I have a transit gateway in US West connected to 2 VPCs, and I have a transit gateway in EU West connected to 2 VPCs. As you can see, transit gateway has route tables. I have 2 route tables per transit gateway, route table 1 and a peering route table. Now, route table 1 is connected to the VPCs. We call it a VPC association. Now, what that basically means is when the traffic originates in the VPCs and reaches transit gateway, Transit gateway is going to look at the routing rules in the routing table to make a forwarding decision. Let's understand that by step-by-step packet flow. So the traffic originates in the spoke VPC, heads over to transit gateway. Now, this is a legitimate traffic which is destined to the remote region VPCs. So I want to route this traffic over the peering connection. So I add a routing rule. It says, hey, if your destination is 192.168, which is my remote CIDR range, next hop is the peering connection. Now, transit gateway is going to look at this rule and send the traffic off over the peering connection to the remote transit gateway. Now, as the traffic comes in from the peering connection, it will look at the peering route table to make its forwarding decision. I want the traffic to be routed to my destination VPC, so I'll add the routes accordingly. Now, the return traffic comes to route table 1. I want the traffic to flow back via peering connection, so let me add those routes. And finally, the traffic enters the transit gateway 1. It uses routing table, peering route table logic, and is now sent off to the destination. Perfect. Now, that was an easy way of enabling connectivity between regions. So all VPCs in one region can talk to all VPCs in other region. But most enterprise customers don't want that. They want more specific scenarios, something like, hey, I don't want my prod and dev VPCs talking to each other. I want segregation, isolation. So let's take an example of a scenario where I want only prod to talk to prod across regions, but I don't want my prod to talk to dev across regions. So this is how the setup looks like. You have prod VPCs talking to prod VPCs in different region, and you have dev VPCs talking to dev VPCs in different region. But if there's a traffic which originates in your dev VPC destined for a prod VPC, it goes to the transit gateway and gets dropped. So this is what we want to establish. Now, in order to explain how this is done, I'm going to use prefix lists. Now, prefix list, as the name suggests, is a list of prefixes. So I create multiple prefix lists, one for US East prod VPCs, for dev VPCs in both regions. Okay, now let's try and understand this by step-by-step packet flow. So the packet originates in one of the prod VPCs, and it's destined for a prod VPC in the remote region. The traffic comes to the prod route table. Now, what was our scenario? If the traffic is destined for a remote region prod VPC, we want to send it over to the peering connection. So we add that route in. But if it is destined for a dev VPC, we want to drop the traffic as soon as possible. So for that, we write a special rule which says, hey, if the destination is dev VPC, send the traffic to black hole. This basically tells the transit gateway to drop the traffic immediately. In our case, it's legitimate traffic, so it makes its way to the transit gateway 2. We populate a peering route table so the traffic can flow to the destination. The return traffic reaches the prod route table in the remote region. We want a similar logic there, where if the traffic is legitimate, it should be allowed back onto the peering connection. We populate our peering route table to make the traffic flow to back to the source. And that's it. So our prod VPCs are now communicating with each other. Let's see how our dev VPCs can talk to each other. So the traffic originates on the dev VPC, goes to the dev route table. Very similar logic. If it's destined to a dev VPC, we want to send the traffic to peering connection. But if it's destined to a prod VPC, we want to drop it immediately. So we add that logic in there, let the traffic flow, make changes to the peering route table to enable the connectivity. The return traffic comes to the dev route table. Very similar logic. If it's destined to dev VPC, send it over peering connection. Finally, make changes to the peering route tables. And the traffic flows back. Good. Now we have prod talking to prod, dev talking to prod. Let's see an example if dev tries to communicate with prod. So the traffic reaches the dev route table. Oh, but we have an explicit route saying, hey, if it's destined to US East prod, send it to black hole. And transit gateway immediately drops the traffic. So now we are able to communicate between dev and prod. We are able to communicate between prod and prod, dev and dev, but not between dev and prod. Perfect. So we saw how inter-region connectivity can be established using transit gateways and also some sample scenarios. Now let's jump into how you can connect your AWS resources to your on-premises data center globally. Now you have two technologies when it comes to connecting from a hybrid standpoint. First is AWS VPN, where you create site-to-site IPsec tunnels over the internet between your data centers and AWS. At the AWS end, we give you a fully managed IPsec termination endpoint on Transit Gateway. This highly durable, horizontally scalable endpoint. It's completely customizable. The IPsec configurations, the cryptographic algorithms, everything is totally controlled by you. Finally, from a routing standpoint, you can use border gateway protocol or you can set up static routing. Now, while VPN is a great way to get started, it's still over the internet and it is plagued by latency, jitter, and packet loss. So for your production workloads and critical workloads, we recommend using AWS Direct Connect. AWS Direct Connect lets you create dedicated fiber connectivity between your data center and AWS. You can get port speeds up to 10 gigs, and you can create multiple circuits, multiple connections to get high availability and scalability. You control routing through border gateway protocol, and it's completely customizable. So you can route traffic as your use case demands. Now let's dive a little deeper into AWS VPN and see how it's configured for global scenarios. Now when you create a AWS VPN, we provision two fully redundant endpoints on Transit Gateway. Those endpoints are characterized by public IP addresses, as you can see in this slide. You create one VPN tunnel per endpoint, so two VPN tunnels. That's what characterizes one IPsec VPN connection. Each tunnel gives you 1.25 gigs per second of tunnel bandwidth. And you can load balance traffic on those two tunnels to get a cumulative 2.5 gigs per second. Now, when you send traffic, it is not going to take a straight path because there might be hops in there which you have no control over because it's the internet. This is more evident when you're sending traffic to a remote region. So when you're sending traffic from North America to Europe, that traffic can take any number of hops, can take any path, and you don't have control over it. So we are seeing latency, jitter, packet losses, which is not an ideal experience. So one way to get around this is to send traffic to your transit gateway in US East, and then from there use inter-region connectivity to send traffic to EU West. While this is perfectly valid way of doing it, as we had discussed during inter-region peering, you don't want to create regional dependencies. So if US East fails, you lose connectivity. Plus, you might have added latencies, and you might it might be a little more expensive. So what we want to do here is reduce the usage of internet and use more of AWS backbone. And we can do that using accelerated VPN endpoints. And the idea here is that instead of creating an IPsec VPN connection from your North American data centers to a remote endpoint in Europe or Asia, why don't I create an IPsec connection to the nearest Amazon edge location? And from there, back to the remote region, it's completely over AWS backbone. So we no longer have the uncertainties of internet. So now you send traffic to the global edge location, and from there, it's all over the AWS backbone. So when creating global designs and architectures, you should consider accelerated VPN endpoints for VPN connectivity to remote regions. And you'll do this from all your different data centers globally. Great. But for production workloads and critical workloads, we still feel you require the performance and consistency which AWS Direct Connect provides. So let's dive into how that works. Now, in order to set up dedicated fiber connectivity from your data centers to AWS, you meet us at what is called the Direct Connect locations. These are third-party co-location facilities where AWS has cages and devices, and that's where you do the physical connectivity to us. Now let's take an example. Let's say you have your North America data centers and you want to connect to us through direct connect locations which are located in North America. So number one, you go ahead and choose two different direct connect locations for high availability and redundancy, which are close to your data center. Next, you create physical connectivity from your data centers to these locations. Now you might have presence in those locations. If not, you can work with a service provider or an AWS direct connect partner to get this connectivity established. You go to the AWS console, request direct connect connections, 1 gig, 10 gig, sub 1 gig. Once you do that, we'll allocate router ports in our devices and then give you a LOA, letter of authorization, which you can use to create a cross connect. Once that's done, now you have physical connectivity to AWS. Our direct connect locations are connected to AWS backbone through redundant fiber connectivity. Now you have physical connectivity, but how do I get access to AWS resources, which is your transit gateway, your VPCs? Now, in order to do that, you need to create a Direct Connect gateway. Direct Connect gateway is a global, isolated virtual router. It sits within your account and it only interacts with your resources. It's completely dedicated for you. It's highly available. It connects to all the transit gateways globally, so it's a global resource. And in order for your routers to communicate with Direct Connect gateway, you have to create a transit WIF and establish a BGP peering relationship. So now your customer router is directly interacting with AWS Direct Connect gateway and they will be exchanging routes. So Direct Connect gateway will learn the routes which transit gateway configures, and then it advertises those routes back to your on-premises routers. Similarly, you will advertise your on-premises data center route to Direct Connect gateway. Once the exchange of routes is completed, you can send traffic from your North America data center to AWS regions globally. All the traffic from the Direct Connect locations in Virginia and New York to the remote location in Asia Pacific is over AWS backbone. You'll set up something similar for your Asia data center. So we are using Direct Connect locations in Delhi and Mumbai. And we use them to send the traffic to remote AWS regions, completely on AWS backbone. Great, so now we understand how you can use Direct Connect to establish global connectivity and send traffic to AWS regions globally. I do want to talk about two things. One is, how do you do that in a highly available manner? And the idea here is that if there is a failure in one of your circuits, you should be able to reroute your traffic to your other circuits. And you should be able to do that in the most optimal way, which means lowest latency and choosing the shortest path. So let's see how that's done. Now, in order to explain that, I'll take a sample scenario. In this sample scenario, your data centers are connected to AWS through different locations globally. North American data center is using Newark, New Jersey. European data center is using a co-location facility, Digital Realty London. And in Asia, you're using STT Hyderabad. You're advertising unique prefixes from these locations, 1.0, 2.0, 3.0. So Direct Connect gateway learns these prefixes from your data centers. Now, if a traffic is destined for 1.23, Direct Connect gateway is going to send it off to New Jersey Direct Connect location. Similarly, if the traffic is destined to 2.56, Direct Connect gateway is going to send it off to Digital Realty London. Now, if that link fails, Direct Connect gateway doesn't have a route to send the traffic which is destined for 2. network. So it simply drops the traffic. So we don't see any high availability. A circuit loss results in packet loss. So in order to solve that, there's an easy fix. In addition to the more exact prefix, also advertised a summarized route. So in this scenario, if there's a link failure, AWS Direct Connect gateway is going to send the traffic to the North American data center because it sees the summarized route 192.168.0.0/18. Similarly, if the New Jersey link fails, Direct Connect gateway can take the packet and send it off to the Digital Realty London location. And this is how you can get high availability. So if one link fails, make sure you have a summarized route in another location which you're advertising, so we can use that location. Direct Connect Gateway is connected to all your locations, so it can route traffic to any of those circuits. So you do get that high availability. But you might be thinking, hey, when my New Jersey link failed, why did Direct Connect Gateway choose the London location? Why not the Asia Pacific location, that's the Hyderabad? And that's where most optimal routing comes in. I want Direct Connect Gateway to choose the shortest path back to my on-premises data centers. Now, in order to explain this, what I want to do is change the scenario a bit. So now from all the 3 Direct Connect locations, I am advertising the same prefix, the summarized prefix. So when the packet reaches Direct Connect Gateway, which path does it take? All the 3 paths look equal because I'm advertising the same prefix. Now, in order to understand that, I want to point your attention to this specific piece from our AWS Direct Connect documentation, which says, hey, there's an AWS Direct Connect location, and that's always associated with an AWS region. What that means is we will always prefer New Jersey Direct Connect location when the traffic is coming from US East 1. We always prefer the associated AWS Direct Connect location to the region. Traffic coming from US West will always prefer Digital Realty London. Traffic coming from AP Southeast 1 will always prefer Hyderabad, because those are associated Direct Connect locations to that region, and that's always preferred. Now, if there's a link failure, traffic will take the next nearest path. And this is a logic which is embedded into our backbone. First, we will always choose the associated AWS region, and if that fails, we will choose the next nearest location. Now, there might be a chance where there are 2 locations which are equidistant. In that case, traffic can be load balanced on the 2 different Direct Connect locations. If you don't want that, you want more predictability, you can use AS path prepends, where you can prepend your routes and make them more expensive. We always will prefer the least expensive route in this case. So here I choose the path through England, which does not have any AS path prepends. So, our journey to finding the most optimal path. Let's quickly summarize it. By default, we always choose associated AWS region. If that fails, we go with the nearest location, but if you use AS path prepends, we will choose the lowest path. Then we choose the other path, and then finally, we choose the location which is the most far, which is Asia Pacific. So we have high availability. We are able to use all the 4 circuits. At the same time, we are able to do it in the most optimal way. Perfect. So now we have seen how global hybrid connectivity can be established and how we can do that with redundancy and with optimal routing. Finally, let's talk about our end users, the most important aspect. So the idea here is I have my application stacks which are deployed. I have transit gateway communicating through inter-region peering. Now I want to expose my application stack to my end users, and I want them to access these stacks with the lowest latency. Now the logic here I want to implement is my stacks are fairly similar which are deployed in different regions. So when a user makes a request to my application, I want to route my user to the nearest AWS region. In order to do that, I'll use DNS. So what I do is I have app1.sidaws.com as my application DNS name. And using Route 53 and routing policies, when a user makes a DNS query, my Route 53 service will return the IP of the application stack, the AWS region, which is closest to the user. And I can do that using 2 different policies. Geolocation routing policy basically directs Route 53 to look at the geolocation information of the IP address from which the request is made and return the IP address of the AWS region which is in the same geography. With latency routing policy, Route 53 looks at the latency information and returns the IP address of the AWS region which has the lowest latency to the end user. But using both these policies, I can redirect my users to the nearest location where I have my application deployed. Now, while that's a great thing, the users are still using public internet to reach my applications. And I don't like internet. We've already seen that. So how can we reduce the internet use and use more of the AWS global backbone? We do that through the use of our Amazon Edge locations, very similar to how we saw with accelerated VPNs. And the idea there is the users can send the traffic to Amazon Edge locations, and from the Edge locations back to AWS regions, the traffic is going over AWS backbone. In order to do this, we need to use a service called AWS Global Accelerator. With AWS Global Accelerator, you get 2 global static IPs, and that is what defines your application. These IPs are advertised over 91 points of presence in 42 countries. Global Accelerator can handle TCP and UDP traffic. You can have your backends as application load balancer, EC2 instances, or even elastic IPs. It has built-in high availability. These edge locations, which you see, are not single points of failure. They have redundancy built in. Finally, it allows for fine-grained traffic control and has built-in health checks, and we'll look at what that means in the next slide. So I have my application stack deployed in 3 different AWS regions. I have edge locations globally, and I want my users to access these edge locations. So for that, I create a global accelerator. I name it SID App 1. I specify a UDP listener. This is the port on which my accelerator will be listening for traffic. I add endpoint groups. So endpoints are basically my target groups where my global accelerator will be sending traffic to. So I add 3 endpoint groups, 1 for each AWS region. Once I do that, Global Accelerator will assign 2 static IPs, and those IPs will be advertised through all the Amazon Edge locations globally. So when a user tries to connect to Global Accelerator, the traffic will be automatically rerouted to the nearest edge location. And from there, all the traffic uses AWS Global Backbone. Now, if there's a failure, if endpoint group 2 fails, as I said, Global Accelerator is doing health checks. So it detects that and automatically reroutes the traffic to the nearest endpoint group, which is endpoint group 3 in this example. Now, I also mentioned there are some traffic policies which you can use. So if you see in North America, I just brought up a new stack, and I can use fine-grained traffic control policies to move my traffic from the old stack to the new stack. If you remember, this is something which is done in blue-green type of deployments. So you can do that using Global Accelerator. Now, while this is great and we have solved a lot of problems, how can we make this even better? And we can do that using CloudFront. So the idea there is we can cache our data in the edge locations. So the traffic never has to go back to AWS regions. It can be served right off the edge locations. And this will ensure least amount of latency. So with CloudFront, you can cache your edge data in edge locations in 220 plus points of presence. We support HTTP and WebSocket protocols. So keep in mind, this works at a layer above where Global Accelerator was functioning. Global Accelerator was TCP UDP. This is HTTP and WebSockets. We support application load balancer, EC2 instances, and S3 buckets as backends. There's a bunch of connection optimizations like connection pooling built in. You can add additional logic by using Lambda functions at the edge. And finally, it supports web application firewall, DDoS protection, and a bunch of inbuilt security. So let's see how this works. So you have your application stack deployed in the United States region, and you want to provide low latency access to your application stack to users globally. So you provision a CloudFront distribution. Using DNS, the users will be routed to the nearest CloudFront edge location. Now, the first request does have to come back to the application stack to extract the information, but all subsequent requests do not require the edge location to send the traffic back to the region. And the data is served right from the edge. Perfect. So now let's recap. So we saw how you can use transit gateways to connect your application stacks globally. We saw how you can do that using additional connectivity scenarios where prod can talk to prod, dev can talk to dev, but prod and dev cannot talk to each other. We also saw how you can connect your corporate data centers to AWS stack using Direct Connect Gateway, and how you can do that with redundancy and optimal routing built in. And finally, we saw how you can provide low latency, last mile connectivity for your end users using Amazon Edge locations, using Global Accelerator and AWS CloudFront. Thank you, and please fill the survey. We would really appreciate your feedback.